It's my great pleasure to introduce Professor Paul Alivisatos. He is Executive Vice Chancellor and Provost in University of California, Berkeley. He's also Samsung Distinguished Professor in Nanoscience and Nanotechnology Research in UC Berkeley, Founding Director of Kavli Energy Nanoscience Institute, and Director Emeritus of Lawrence Berkeley National Laboratory. His work has contributed greatly to the fundamental physical chemistry of nanocrystals with a lot of accomplishments, including studies of scaling laws governing the optical, electrical, structural, and thermodynamic properties of nanocrystals. So I think it's a waste of time because I'm sure he's the one of the most famous researcher in nanoscience and technology, and everyone here know who he is. So with that, I'd like to welcome Professor Paul Alivisatos.
Oh, thank you so much. Can you hear me okay? Am I connected all right?
Yes, I can hear you very well.
Thank you so much. Yuri Gogochi just gave a beautiful seminar. I was so happy to hear it. And also, I too, last night, I watched the Elon Musk Battery Day video. Here in California today, we have terrible climate change impacts. Enormous fires all across the state are really devastating our area. And we see climate change in such a direct way. I'd urge you, if you are interested in the future of materials, to take a look at that very nice Battery Day. It's on YouTube. You can go see it. All of your coworkers can see it. It's quite beautiful. Let me start by sharing my screen. Am I screen sharing okay?
Yes, we can see it very well.
You can see my screen? Okay, thank you very much. Okay, so I'm so sorry that I cannot be there with you in person. Obviously, the global pandemic, the COVID-19 has changed everything in so many dramatic ways, and it has kept us apart from each other. But thank you so much for creating a way we can be together remotely and still share our results and our science. I was going to give a presentation about a more broad topic in my research group concerning light-emitting materials. But actually, as I thought more about this a couple of days ago, I thought maybe I would do something a little bit different, if I may. In March, my research group had to shut down for almost 4 months. And then since then, we have been using the laboratory, but in very limited, very different than the way we used to before. And so during that period, my coworkers and I have been working very hard to take research which had been going on in the group already, but to accelerate it via using the techniques of data science and machine learning. And so I thought today I would share with you some unpublished, all of these results are still unpublished, that concerned the things that we've done since COVID-19 occurred. And we had to shut ourselves down. And so I'll talk a little bit, although now that we are back and doing experiments, but I will talk a little bit about a set of experiments that all take place in the liquid cell TEM. And so we'll show a little bit of some deep learning analysis, neural networks to understand our data, some aspects of controlling the chemical environment inside a liquid cell in the TEM, and also a way to analyze TEM images in an unsupervised way, meaning we do not tell the computer anything about the sample we have. We simply let it try to discover. I hope that when I'm completed with this presentation, that I'll at least have reaffirmed for you something you probably all know, which is that nanoscience has always had a key component in developing new ways to visualize on the nanoscale, new tools for seeing. And many of those experimental tools use new detectors and other kinds of techniques that are generating these days vast amounts of data. And so the emerging tools of data science, artificial intelligence, machine learning, all of those will help nanoscientists to leverage these new tools and to greatly accelerate discoveries in nanoscience. At the same time, while the new data science tools are really interesting and they're different methodology, at the same time, of course, our core fundamental knowledge, if you like, classical approaches to physics, chemistry, and material science, all help define and answer some of the most interesting questions in nanoscience. So I will try today to show what we have been doing in this area of using data science in order to understand a new experimental technique for visualization. In our case, the technique for visualization is one that we have been investigating in my research group since approximately 2007. I believe our first papers were published in 2008. So it's getting to be a while now, 12 years. And during that time, we have been able to create environments where very, very thin layers of liquid are trapped between membranes, which an electron beam can penetrate. And then in that small environment, we can now look at things moving around inside a liquid. And so we can see, for example, the growth of nanoparticles and visualize it in a way that was never possible before. We can measure the forces between nanoparticles. Jung Park, who's now at SNU, when he was working in my research group, did remarkable work, and he continues it now at SNU with very wonderful papers, understanding the individual atomic level structure of nanoparticles using the liquid cell. Chemical reactions, controlled etching. We can observe DNA-linked nanocrystals, which suggests that we should be able over time inside the liquid cell in the electron microscope to also image proteins, membranes, and other biological systems. And of course, we can look at other processes like how nanocrystals, which are artificial atoms, can join together to form artificial solids. So it's clear that the liquid cell electron microscope is a very powerful tool for nanocrystal science, and one that could become extremely important in the next 10 years. We have then applied the tools of these tools of data science to see what will it teach us. And so I will show you 3 examples now. In the first one, we're simply going to do the absolute simplest experiment possible. We have a gold nanoparticle in a liquid cell, and we are irradiating it with the electron beam and imaging the position of the particle. It's in water, and the particle tends to stay fairly close to one of the electrodes because of the interaction potential between the nanoparticle and the surface. And we just want to see at the first, what does the motion of the nanoparticle look like in the liquid when we have when we are interrogating it with the electron beam? And we have studied this for many years, so have several other research groups. But one thing that has been very difficult has been to try to really test in some detail what happens when the electron beam is more flux, more intense electron beam. So here you can see an experiment that we have done recently, and this shows well, let me make sure I get here my laser pointer. I'm sorry. Here it is. Pointer up, laser pointer. There it is. So here we have a set of panels which show the for a fixed time interval, we observe a nanoparticle for 30 seconds in the electron microscope, and then we turn up the intensity of the electron beam, and you can see that it hardly moves at all on the length scale of this plot. But when we get up to the high flux of 49 electrons per angstrom squared per second, then we start to see it really moving and covering a large range. Furthermore, if we take each one of these panels and we expand it spatially, not at the same time interval anymore, of course, the time interval will change because the particles move different amounts. The displacements are so different at the different e-beam fluxes. But if we look carefully at this, what we can see is that the particles move in ways that seem to suggest very different patterns of motion. It looks like the mechanism of the motion must be changing as the electron beam is becoming brighter. Now, this is a very important thing, because if we want to understand the intrinsic nature of the interaction between the particle and the surface, we need to be able to remove the effect of the electron beam. And if for some reason we may wish to change the motion of the particle in order to, for example, examine active matter, then we would like to know how the electron beam might influence things. So it turns out that there are three mechanisms that people have talked about for many years that could be relevant to this kind of motion. The first one is, of course, simple Brownian motion. In other words, the particle moves near the surface, and it makes, under the influence of thermal, of temperature, it simply makes a series of random Gaussian steps that are not correlated with each other, and that will, of course, lead to Brownian motion. There could be a situation of what we would call fractional Brownian motion. And to get a sense for that, imagine a situation where a Brownian particle is moving within a certain zone, but it's inside a gel or some other viscoelastic medium, and therefore it cannot always move in random directions. Sometimes it's pushing up against the gel, and therefore its next step is more likely to be in the opposite direction of what led the particle to collide with the gel. And therefore the steps, although they still are Gaussian, because of temperature, they will have a heavy component of anti-correlated steps. In other words, if one step is in one direction, there's a greater probability that the next one will be in the opposite direction. Another model is what's called continuous time random walk. Imagine, if you will, that the surface somehow has a few places that can very strongly bind a particle. In that case, we might see a trajectory where a particle stays in one position for quite a while, and then all of a sudden it makes a big jump and leaves. And those steps will now no longer be correlated, and indeed they will have what's called a heavy-tailed non-Gaussian displacement and a heavy-tailed waiting time. In other words, they'll have the steps are not all equal in time. Sometimes they sit there at one spot for a long time, and then suddenly there's a motion. So both the displacements and the times are no Gaussian displacement. So while we were in the COVID-19 break, my colleagues, Veda Jamali especially, and working with her colleagues, has developed a neural network. We call it MoNet, and the MoNet neural network takes hundreds and hundreds of these images. Every trajectory is then analyzed based on whether the most likely distribution of motions in the network looks like fractional Brownian motion, or Brownian motion, or continuous time random walk. And so we're able to then take vast amounts of this data and then see which model is this most consistent with using this neural net method. And you can see here some results from that. And what we see is these are for 30 particles, 373 trajectories of 30 frames, 300 frames each. This is a lot. I mean, in the past, this would have been really very, very difficult for a human being to do. But this is done, of course, relatively straightforwardly with this instrument. And what you can see, I think, reasonably clearly is that that the probability that these are Brownian motions is actually fairly low at all dose rates. But that at very low dose rates, it appears that we have a fractional Brownian motion. And at high dose rates, it looks like we have a continuous time random walk kind of motion. We can verify that by looking carefully at a number of detailed characteristics of these trajectories. For example, we can look at how the mean square displacement changes as a function of time. or we can look at the distribution of displacements. This green curve here is a Gaussian distribution. And you can see that even at low fluxes, there is a deviation from a Gaussian, which is consistent with the fractional Brownian motion. But at the high dose rates, we see this heavy-tailed distribution. It's not Gaussian at all, consistent with continuous time random walk. We can look at what is the probability that a particle will be in a similar place at a later time. And if we do that for different time intervals, 1, 2, 4, 8 like this, what we see is the clear signature of an anti-correlated motion in the low flux regime, which is, as I mentioned to you, it seems as though every so often if the particle moves in one direction, it's more likely that it will move in the opposite at a later time. That is very much not the case for the case where the electron beam flux is very high. So this method has allowed us in some kind of reasonably objective way to take a vast amount of trajectories and then classify them and extract a mechanism for motion. Now, ultimately, we would like to have a chemical explanation. Why does the particle experience this? And one thing that we think is probably the case, although it's not yet really, something we've been able to prove, is that we create a set of locally charged sites on the surface when we irradiate with the electron beam in the way that this cartoon suggests, and that those locally charged sites are the ones which act as the trapping sites for the high flux continuous time random walk, and that at low flux, the very dense network of the hydrogen bonding and the network with the surface of the silicon are what create a kind of viscoelastic network that make it be a fractional Brownian motion. This part, of course, now remains to be proven, but we now know the two mechanisms and we can go through and try to understand them better. Okay, I'm going to switch now to a slightly different topic, and in this case, we will not use so much the tools of data science, but I will try to illustrate how we still, even in a period where we have all of these advanced techniques, just going back to some very simple ideas can help us to continue to learn and advance our understanding of what happens. So in this case, we will have nanoparticles of different metals, and we will place them inside the liquid cell. And then inside there, we will put a chemical species which can etch the nanocrystal, can remove atoms from it oxidatively in this case. So we're going to have, for example, gold nanocrystals, which when we have iron chloride present, will act to etch a gold nanocrystal. And this is a project we've worked on for many years. It's kind of our model system for understanding the chemistry inside a liquid cell. Remember, in the liquid cell, we have a very, very thin layer of liquid, and it's being irradiated with an electron beam that has an energy of a few hundred kilovolts. So there's a high energy electron beam passing through here. And that beam can, of course, create all kinds of chemistry inside the liquid environment, and that chemistry can act to etch the nanoparticle. And so we try to understand this liquid environment. It's a very complex one. Ultimately, a measure of success for us would be if we could do something so that inside the liquid cell, it behaved as if we had an electrochemical electrode where we could set the chemical potential inside the liquid cell. So I'm going to show now some experiments which we believe indicate that we have found a way to do that in a very simple way. We have present inside the liquid cell, this is the work of Ivan Moreno-Hernandez, we have present inside the liquid cell now, we add a redox couple. In other words, we add a molecular species, vanadium oxide, VO2 plus, Cr3 plus or cerium 3 plus. We add these cationic species in, and they can be oxidized and reduced inside the liquid cell. as a result of their reactions in the presence of the radiolysis environment that creates hydroxyl radicals. So now we can take here a nanoparticle, let's say, and we can simply observe that nanoparticle of gold being etched. And we can do that either with vanadium oxide, the chromium, or the cerium. And I think what you can see very clearly is that in the presence of the cerium redox couple, we get a very rapid oxidation of the gold. It disappears very, very quickly. Notice this is 4 seconds. In the presence of the chromium, the time scale here is 16 seconds. And you can see there's hardly any change in the presence of the vanadium oxide over a period of 50 seconds. So it's a much, much, much slower, unobservable on this time scale. If we go and look carefully at the redox potentials of these, they actually can make a great deal of sense because the cerium is the one that's at the highest oxidation potential, the chromium next, the vanadium the lowest. So it appears as though by adding this species, we have set the redox potential inside the liquid cell. It's going to turn out to be quite important for us to be able to do that. For example, perhaps one day we wish to put a protein inside this liquid cell. We don't want it to be immediately destroyed, or we want to put in another species. And so if we are able to establish a kind of set of chemical additives which allow us to adjust the oxidation potential inside the cell, it could be extremely useful for us in our research. Here's an additional kind of line of evidence for this. We can take, for example, and have present simultaneously a gold particle and a platinum particle. And then we could put in different redox species. So it's the same environment chemically, and we can set the potential now, depending on which redox species we put, such that the gold will be etched, but the platinum will not be at all. And vice versa. We can really move this around quite extensively. What I think you can see here is that, for example, in order to be able to etch the platinum, we need to put the cerium, the highest oxidizing potential redox couple present. But if there's only chromium or vanadium oxide, there will be no etching of the platinum. If we're at the chromium case, again, the platinum is not etched, but the gold is. And if we go to the vanadium oxide case, then neither the gold nor the palladium is etched. So indeed, it looks like we can do that. And here you see an example where we have taken a particle that has both platinum and both palladium and gold components to it. And we are able, it's a particle that has this kind of core shell-like structure. And we are able to selectively go in and etch away one of the components while leaving the other one completely intact. So that's just a kind of demonstration of the ability of controlling this local redox potential. Now, I mentioned to you that we had been studying these kinds of systems for a very long time. And in the course of all those studies, what we have been looking at is how various iron species are involved in etching the gold. That's a classic system. We've published papers for several years on it. I won't review them right now, but suffice it to say that if we add iron chloride or iron bromide or iron iodide to a solution that contains gold nanoparticles in the liquid cell, and we might have, for example, these two graphene layers and an electron beam passes through there, then we would like to know, based on what I just showed you with the redox couples, we would like to know a little bit about what is the chemistry that goes on inside here. And in fact, almost in a sense, we're starting in these works now to invert this and to say gold itself serves as a probe of the chemical environment inside the liquid cell. We can make variations inside there, and what happens to the gold can become a kind of diagnostic for what's inside the liquid cell. So here you can see a few experiments that have been done recently by Michelle Crook. And what you can see here is a case where if we have no iron chloride present, there's absolutely no etching of the nanoparticle. So it's a little bit like what I showed you before. Clearly, some kind of redox couple corresponding to an inorganic species like an iron is essential to etching the gold and to making that a possibility for it to occur. And what you can also see here is that if we change the halide ion from chloride to bromide to iodide, then as we go from chloride to bromide to iodide, the etching speeds up enormously. In fact, so much so that if you look here at the iodide case, you can see very clearly that the etch rate is so fast that it starts to peel off multiple layers of the crystal all at once. It becomes a very rough particle. It's kind of entered into a roughening regime etching mode when we've really got the fastest etching in the presence of the iodide. And so the question becomes, we know clearly that we need the iron cations. They must be fundamental to this etching, but we're not yet sure what it is. What is it that these halide ions are actually doing inside this system? So in this case, we've turned to another very classical experiment. We're working now with Alex Kant and Wolfgang Nolli at the Leibniz Institute of Surface Engineering in Germany, where they can do post-radiolysis studies. Perhaps you'll know that if we place a lot of energetic particles through water, it doesn't really matter if it's electrons or if it's some other kind of fundamental high energy particle. Almost any of them passing through water will create more or less the same chemical environment after a little while that's present. So we can use at a bulk scale pulsed radiolysis to probe what happens inside a liquid environment of water when we add different chemical species present. And one of the things that we can see very clearly in those kinds of experiments is the presence of a very strong photo bleaching at 340 nanometers. 340 nanometers is of optical absorption, UV absorption, is where the iron 3+ species absorbs. So when that species kind of slowly disappears in the post-radiolysis, or not so slowly, it means that the iron 3+ is being transformed into some other highly oxidizing species. And that actually makes a great deal of sense. The iron 3+ is being oxidized, and we believe we're not quite finished yet identifying specifically what that oxidized iron species is. But that's the species which actually has enough oxidation potential to etch the gold. The iron 3+ doesn't actually, and that's been one of the big mysteries for us. When I showed you the earlier work with the redox couples, for a while it appeared it was confusing to us because iron 3+ shouldn't have enough oxidation potential all by itself. But when it's placed into this higher oxidized iron species, it surely does. The other thing we were able to do is an experiment in the electron microscope now, where we create that highly oxidized iron species, and then we simply turn off the electron beam. And when we do that, we see that the etching actually continues for a very long time. There would be absolutely no etching if we had not first introduced the electron beam, and of course, the iron is required. So at this very low dose rate, the fact that we continue to see, it's enough to be able to see the particle, but not enough anymore to be able to do any of the chemistry that would normally modify it. It means that the species, like the one created in the pulsed radiolysis, must also be present here and is continuing to perform the etching after the electron beam has effectively been turned off. So in the end, what we believe is the correct mechanism for this is to create a highly oxidized iron species, and that oxidized iron species is what is then oxidatively etching the gold. And then the question of what the role of the halide is, all of our available evidence suggests that what happens is that these halides are forming complexes which are with the gold. You form a gold chloride, gold bromide, gold iodide species, and that indeed the iodide species just has a much stronger binding energy with that gold plus ion in solution compared to the gold chloride. So essentially, the iodide is almost pulling the gold atoms out because it binds to them so strongly. compared to the chloride or the bromide. And so we believe that's actually the mechanism of the oxidative etching in this case. Perhaps I just leave it as a comment to say the consequence of this is we ought to be able to now to begin to be able to etch much more sensitive species. And here's an example of this. We haven't done a whole lot of this kind of work previously, but semiconductor quantum dots, which of course we work on a great deal in my research group and have for more than 30 years, our interest certainly is to be able to etch those and use them to try to understand the surface stability and other characteristics of these very tiny small crystals. And so Cheng Yan and Gaurav Kamath have been working for a while now to develop the right conditions for doing that. There are some tricks to it. It's not one of the easier experiments, but we do have it working pretty consistently now. I'm not showing any movies here, but we have developed a very large set of etching experiments on these lead selenide nanocrystals in which we're able, again, to set the chemical potential inside the liquid cell sufficiently low that this very, very, very sensitive species, we can observe the trajectory of its etching. Whereas I would say 2 years ago, 3 years ago, we'd put these things in there and they would just be gone before you had a moment to even look at them. So we're getting closer and closer to being able to turn up or down the oxidation potential in the liquid cell. Okay, I'm going to show one last example of some recent work. And this is now not in a liquid cell per se, although I'm quite sure we could use it there. But it's just another example of the data science tools helping us out a little bit inside the research group, and it's a project we did during the COVID-19 shutdown. So what you can see here is we very often will make a set of nanoparticles, and they're not all the same. Some are different shapes, or maybe they are almost all the same shape, but we're never quite sure. When we look at an electron micrograph, have we really seen all the particles? Do we really know that we've made a perfectly all one shape, or have we got some distribution of them? So what we have now is an algorithm which will take very large numbers of images from the transmission electron microscope of a nanoparticle sample, and it will detect the edges by the contrast change as it encounters the particle, and then we will classify the particles according to a number of classifiers. The area, the eccentricity, the aspect ratio. A sphere would be 1 to 1. A rod would have a large aspect ratio. The circularity, the solidity. And in our case, we are only going to do this case for convex particles. There are, of course, many concave particles. We're developing a different approach towards that. But at the moment, this is only for convex nanoparticles. And so we have this series of classifiers, and we take all of these particles, and we do a kind of extraction of the particles to avoid ones which are overlapped from each other. And we're now going to have an algorithm. It's an unsupervised machine learning algorithm. What that means is we do not tell it anything about what particles are present. We simply allow the algorithm itself to tell us how many different kinds of particles are present based on the combination of all of these classifiers. And you'll see now what something like that looks like. So here's a sample where we've taken two sizes of nanorods and mixed them together, 50-50, and we've simply applied this algorithm to it. And it's an algorithm in which we want to minimize the entropy of the selection process. And you can see here that this particular algorithm did an approach where the absolute minimum says there are 3 different kinds of particles. That's a little bit better than if we say there are only 2. Remember, we started with nominally a pure sample of 2 kinds of rod. We mixed them together and we said, well, how many different kinds of samples are there here? And it's come back and told us, yeah, it does look like there's 2 kinds of rod here, but actually there does appear to be a minority. It's not as many, but in all the many images that were collected, it also observed that there's a subclass of particles. And you can kind of see here when we stack them all up against each other, what the relative amounts of each of them were. And you could well appreciate that it might be possible to kind of, underestimate how much of this is present when you just look at a select number of images like this one. And you can see here the classifiers, and I think what you can see is that if you only looked at one classifier, like the area, or you might get a very different answer than if you were to look at one related to circularity, or aspect ratio, or eccentricity. And remember, this method looks at all of those and how they correlate with each other, and that is what allows it to classify the particles without us having told it in advance what they are. And it does quite well if we compare it to what a human being would do. Human beings did this and they compared, and it's really quite indistinguishable. So that's encouraging. We have another example where we've taken triangular prisms and done the same kind of thing. So here you can see our first pass at what has been a literature preparation that's been out there for some time, which makes triangular prisms of gold. And so in the first pass, it came back and it said, well, it looks like there are two kinds of shape. But I think you can also see here, it's a little bit ambiguous exactly what's going on. And so it's possible for us to take these fractions and then perform this analysis a second time on it. So if we take, for example, that green fraction, if we go back and look at it carefully, perhaps what you can see here is there are some particles, like for example, let's say this one right here, it's very, very triangular. If you look at this one, it's got more rounded edges, and here they're even flattened a bit, and some of them look like they're almost heading towards being a hexagonal shape. And of course, I think we could kind of move smoothly between a triangle and a hexagon by alternating short and long and making the short ones longer and longer. Eventually, it would become a hexagon. So it's a real question to ask, is that going on inside the sample? And we can take it then and perform another pass on this sample. And now what we'll see is that indeed there seem to be an additional set of fractions inside here. If we did this in the previous experiment, a second round, it doesn't change the number of classified particles present. But in this case, it really does. It indicates that this sample has a little bit more complexity to it than what you might think just from saying, oh, they're triangular prisms. It's a little bit more complicated than that. There's more going on. In fact, we can take an enormous area of samples and then classify them again. And they go from triangular to hexagonal. I think you can see they're really a great deal more hexagonal down here. And this is kind of what the transition zone between those two looks like. And we're not really, we haven't completed an analysis on this. We're doing a lot of theoretical work with this right now. But what it suggests to me, at least, is a strong possibility that this rounding of the edges may be an intrinsic feature of what goes on in the synthesis. The energy change going from these triangular shapes to these hexagonal ones is relatively modest, but the width of this zone may characterize that, or there may be other aspects of the kinetic pathway that kind of dictate how this shape is really wanting to form. I think, I'm going to kind of wind it down here. I decided today, as I mentioned to you earlier, to just share with you some experiments that came out recently from the group. They're all still unpublished, they're in development. One of the reasons I was motivated to do that is because of just what enormous change it's been for all of us around the world to have been in the midst of this giant pandemic. It's changed how we interact with each other. But I am also feeling, when I think about the experiences as a scientist that I've had during this period, the fact that we had to leave the laboratory for a little while has turned out to be really interesting, because during that time, we had to struggle to see, well, what are some new things that we can do with some of the data sets we have? And we've learned a lot about how to go back into our data and use some of the data science tools. I'm quite convinced that these tools of data science will be very, very powerful for us, and that they will make all the difference in the world between taking the liquid cell TEM from an observational tool to a quantitative tool. I'm certain that they will do that. But at the same time, it's not as though I believe, well, these data science tools, that's the answer to everything. I think in the end, really going back to our basic chemistry principles, thinking about things like what goes on inside a redox couple, those remain. And so to those of you who are kind of early in your careers, I would say, you know, trying to adopt a new set of tools to learn them, but then to try to be aware of what the underlying kind of classical ways of thinking and combining those together. Why that's a way I would strongly suggest that you try to take advantage of this big revolution in data science that's going on if you're in the materials or nanoscience area. I'd like to just acknowledge these people. I mentioned Vida Jamali. She developed all of the work on the neural network profiling of the trajectories of motion, the fractional Brownian motion, and the continuous time random walk, the study of correlated and anti-correlated motions inside the liquid cell. Michelle Crook did the work on the iron chloride mechanism. Ivan Moreno Hernandez has been the person thinking from an electrochemistry perspective, how can we set the oxidation potential inside the liquid cell, which I think will open up many doors for us. And Jingji Wang has done all of the work developing these unsupervised algorithms where the TEM images are analyzed without us saying in advance what the shapes in the material are. And I'll stop there and just open it up for some questions.
Okay. Thank you very much for very nice talk, Professor Paul Alivisatos. So it's time for the question. So I can find some question in our Q&A chat window. The first question is by Jehan. Thank you for a great talk. I may have missed your explanation, but from the second part of your talk, why the gold selectively etched over platinum when platinum is less noble than gold? Why platinum?
Yeah, it has to just do with the oxidation potential of the redox species that's present and the potentials at which they, I should be a little bit careful here, it's more complicated. The overpotential that's required for platinum and gold are not the same. So the story, thank you for the question, it is just a little bit more complicated than what I explained here, and Ivan has a whole lot more experiments actually to address the issue that you explained, that you ask about. But it turns out that the overpotential for etching gold and platinum are very, very different kinetically. So I portrayed this as being exclusively about the oxidation potential, but it's a little bit more complicated than that. And there's some experiments I didn't really have a chance to put in here that kind of offer some better explanation for that. So it's true that you require somewhat different overpotentials for these two to get any kind of reasonable rate for the etching.
Okay, the second question is about the automatic nanoparticle profiling algorithm is an excellent concept. Do you have any plans to release it to the public, whether commercial or non-commercial?
Oh, yes. I believe Jingji Wang is about to post a version of this on ChemArchive soon. And it will be, the work that I described will probably very soon be in a peer review. And we will certainly release the software in its entirety so that it can be used by others. And we're also, as I mentioned, pretty far along in trying to make further generations. For example, we study very frequently in my research group tetrapods and other kind of structures which are not strictly convex but are concave in some parts. And we're trying to develop the algorithms for that in the near future. But yes, absolutely, we will share it. And we hope that you use it and are able to find all the shapes in your samples and know. For me, I think this is a very important thing. We've been trying to grow very uniform nanomaterials for a very long time. And I actually think we really don't know enough about what the purity of our samples is. We just haven't had, and it's very hard to do in a transmission electron microscope, because as you probably know, often similar shapes will form large regions where they stick together because they can pack better, and they'll just appear on your grid in a certain zone. And then there may be other parts of the grid that are having other minority shapes that are present in your synthesis, but you're just not seeing them in the few TEM images that you've observed. And what's great about this is you can go through and just do huge numbers and pick up, you know, the species which you might have missed otherwise.
Okay, so the last question is, I think, more technical question. Thank you for your great talk for redox environment experiment with gold. Were the experiments done under low acceleration voltage or low total dose to minimize the knockout damages of gold atoms?
Yeah, the images were done at 200 kilovolts, but and the fluxes that I showed on those graphs. But I will say that absent, for example, perhaps you saw the experiment with the iron, with no iron added, there was absolutely no etching. Or when we had, you know, the appropriate redox couple there, we could just have the sample absolutely sit there really for very, very long times, and there's no etching. So I don't believe we're damaging the particle directly with the electron beam. But of course, we are generating a lot of radical species. And maybe the theme of what I was trying to show is that the we can add in some redox couples to adjust the potential inside the liquid cell, and then it becomes a more predictable kind of environment.
Okay, so time's up. So I'd like to thanks again for the Professor Alivisatos for the great talk. Thank you very much.
Thank you so much, and I hope you all have wonderful discovery in the coming years. So take care and bye-bye.